Hey guys, today I have got an interesting 3D scan from a viewer. It's the spoiler from an AGV Pista performance helmet. The spoiler was scanned with the Creality Raptor Pro, and the challenge for him isn't the 3D scanning, it's the reverse engineering. This part has no flat surfaces at all, which made it tough for him to create a smooth, continuous loft in CAD. In this video, I walk you through step by step how to model this spoiler with smooth continuous curve using BricsCAD. Then I do a test print just to see how the model turns out. This spoiler is pretty expensive. The original part retails for about $130. This video is purely for educational purposes in reverse engineering. I don't encourage anyone to replicate patented products. Let me give a quick overview of the Loft command. If you have at least 3 similar 2D sketches arranged along a curved path, the Loft command will automatically generate a smooth, continuous surface, no guide rails needed. But when you loft just 2 sketches at a time, it only creates a segment. To make the path curve properly, you will need to use a guide rails. This applies to all CAD software, I know, including FreeCAD, but I'm not using FreeCAD in this tutorial because some sections still require lofting with guide rails, and I won't be able to finish the model. Here's my modeling plan. Since the part is symmetrical, I'll start by creating a mirror axis. I will place it using the midpoint of a line drawn across the spoiler's extreme edge. Next, I will create multiple cross sections along the spoiler's continuous curved body, and I will model the part without using guide rails. There is an edge here that isn't continuous, so I will create a separate loft body to handle it. The third section is more complex. It's a 3D hook shape that runs along the side, similar to a glass frame. I will need to loft this part step by step using guide rails, and it takes 8 cross-sectional sketches to complete. The spoiler's wall thickness is quite thin at 1.4 mm, so I will increase it to 2 mm. That way, it can be printed on an FDM printer without breaking. In BricsCAD, I'll begin by importing the point cloud. Then I'll set the point size to 1 for better visibility and use the 3D rotate command to flip the point cloud so it aligns parallel to the XY plane. Next, I draw a horizontal line followed by a reference line across the spoiler extreme edge. Then I use the align command to match the 2 points of the reference line with the horizontal line. Now the point cloud is perfectly aligned to the x-axis. I will repeat the same process to align the point cloud with the y-axis. This is the most accurate approach to align 3D scan data. Next, I move the midpoint of the reference line to the origin point. This is where I will create the first section sketch. Since this section lies on the mirror plane, I will simply flip the UCS X and Y axis by 90 degrees to create the sketch plane. I should also mention that the point cloud download link is included in the description. For this section profile, I will omit the mounting hole and build it later. The profile I'm creating is thicker than the original, so I will set the wall thickness to 2 mm across the entire model. For the second sketch profile, I will create the sketch plane using the UCS 3-point method, snapping it to the cutting edge of the point cloud. The same applies to the third profile. This method lets you create a 2D sketch directly on top of the cropped point cloud, and the accuracy is extremely high. I'm testing the loft model, and you can see there is a gap between the second and third sketch profile. So I will add another sketch profile in between to close the gap. For this part of the model, I won't use guide rails because I want the loft body to be as smooth as possible. Now we have an issue here. The loft profile differs too much. The previous profile has a round top edge, so the next one also need to include that round edge. Otherwise, you have to force the shape with a guide rail. Here I'm creating another profile. I'm lofting 3 profiles over a sharp edge, but the result turns out rounded. When you encounter a sharp edge, you need to split the loft into 2 sections. Each section needs at least 3 sketch profiles to create a smooth, continuous loft body. Now I'm testing 2 loft sections over the sharp edge. By separating the loft into sections, the sharp edge is preserved. Now I'm modeling the hook section. Since this part changes shape within a very short distance, I need to create multiple profiles to replicate it accurately. This section requires guide rails because the profiles differ too much and need rails to form the surface correctly. The guide rail is a spline with 2 control points. You can create it easily by making the UCS Z-axis and drawing the spline along the polar tracking line. Here I'm only testing the loft profiles, not creating the final loft yet. I will generate them all at once after finishing all the sketches. First I will test the loft without guide rails. This way you can clearly see where a rail is needed. This way you don't end up adding more guide rails than are actually needed. This end hook is quite complex. It curves across all axes. This profile doesn't even need a guide rail. There is a mounting hole here. You can't get a perfectly round shape with guide rails, so I will trim it out later using a cylinder. Sometimes when you can't move the control point in the required direction, you can rotate the Z-axis by 10 to 45 degrees. The polar tracking will rotate along with it. You should also check the continuity between the 2 loft sections. If they don't blend smoothly, you will need to adjust the spline. In BricsCAD, you can't force tangency on a 3D spline, but the option is available in Autodesk Inventor. Don't forget to check tangency in both axes, since this hook runs like a spiral. This will be the final loft section. Since I have already tested all the loft sections, now it's time to create them for real. I have placed the created solid on a separate layer shown in gray. The sketches are on another layer in orange, so I can toggle them on and off easily. For the tip of the hook, I will simply extrude it and then cut it into shape using the sketches. Now I'm joining all the hook sections together using the union command. I make another trim on the top of the hook so it forms a smooth, even curve. Now I'm trimming out the hole using a cylinder. Now I'm extrude cutting the body that extends beyond the mirror plane. Now I'm joining the remaining body together using the union command. Then I mirror it to the other side. Now I'm going to model the housings for the mounting hole. This part is more complicated. I'm creating it as a separate body. Then I will join it into the main one. This loft defines the outer wall, while the inner wall will have a different shape. This is the inner wall, which I will use to cut and hollow out the outer wall. Now I'm creating the expansion joint. Without this joint, the spoiler could crack when fitting into the helmet. The reverse engineering is now complete. Tracing thin slice point clouds is the most accurate approach. With the Raptor scanner, the point cloud wall thickness is less than 20 micron, and the overall accuracy after reverse engineering can be under 50 micron. Next, I will export this as a step file and place it into the render scene. The black model represents the reverse engineered geometry, while the white one comes directly from the Raptor scan. The CAD model is smoother and more complete in the hook area. Looking at the curve on the back side, it's even smoother than the original scan. This is the reason we do reverse engineering, because the goal is to produce a part that is just as good or even better than the original. In this case, the reverse engineered spoiler has a thicker wall for FDM printing. That's something you can easily adjust in CAD, but you can't add wall thickness directly to a mesh scan data. Next, I print this out to see how the loft surface looks when printed. I print the part in this orientation because it requires less support and has a larger flat area, plus the hook opening will point upward. Since this is just a test print, I will use PLA. The estimate printing time is about 5 hours. Here's the comparison between the printed part and its supports. The print looks very smooth with no visible edges. I think this part can be used without a top coating. This stiffener is curved, so when printed, it forms a turret step surface. The mounting hole here looks fine and should hold up well, but this part of the hook is prone to breaking. The layer lines can induce cracks. Here are my tips for creating smooth surfaces with the Loft command. Thanks you guys for watching. I'll see you in the next video.